What's up, all you cool cats and kittens? Here we are, pre-calculus. This video is on finding limits with graphs. Get ready for a wild ride. We're going to take a look at so many graphs in this video because so many different things can happen when you're talking about limits. So let's just dive right into, first off, remember what the definition of a limit is. So suppose that f of x is a function defined on some open interval containing the number a. The function f of x may or may not be defined at a. That doesn't matter. Maybe there is a point at a, or maybe there's not. It doesn't really matter. But the limit notation is this. The limit of f of x as x approaches a equals L. And it's read exactly how I just said it. The limit of f of x as x approaches a equals the number L. And what this really means is that we're asking you as x gets closer and closer to a, but not necessarily equal to a, what is the corresponding value of f of x gets closer to L? So I know it's a little bit confusing, so let's kind of dive into it just a little bit more to make sure you guys truly understand this. So keep in mind that the solution to a limit problem is a y value. Okay, so when you're talking about, hey, what's the answer to the limit? It's going to be a y value, not an x value. We're not asking you the y value when x equals a, because that may be undefined, does not exist. Now, it's important to maybe consider or to at least examine, hey, is there a y value at x equals a? But don't count on that always necessarily being the answer. There's a lot more to limits than just that. But instead, we're asking, what is the y value as x gets really, really close to a from both sides? So don't focus on so much as, what is y when x is a? We're focusing on what's happening to y as we get really, really close to a. So we can explore this value from simply looking at a graph of the function. So really, I actually think that it's easy. The easiest way to answer limit questions is by looking at graphs, but you really just have to be trained, right? It's like anything else. You have to be trained in the art of doing this, and hopefully that's what you're going to learn in this video. So here's a couple things that you need to ask yourself when you're asked to find a limit. So first, ask, what is f of x at x equals a? So what is y? Now, please keep in mind that f of x is just a fancy way of saying y. So you're saying, hey, what is y at x equals a? Now listen, this may or may not be your answer. There may be a point there, may not be a point there. It could be undefined. But it's worth at least examining that, okay? And you'll see why when we take a look at some examples. And then the other two questions we want to ask are very similar, but one is saying, okay, what's y getting closer to? Remember, f of x is just y. What is y getting closer to as we approach a from the left? And then we're going to say the same thing, but from the right. So what is f of x getting closer to as we approach a from the right? So we're going to be kind of like, what I do is I kind of put my fingers on the graph, and I start to get closer and closer to a from the left and to the right, and I find out where are my fingers going. So it's important that you understand that whether or not there is a y value at x equals a does not impact if there's a limit or not. The answer to a limit is a number L, but it's not necessarily where you're at x equals a. It's what happens as you approach it. And we're going to see that as we look into really just this first video here, this first problem here. All right, so we see this graph here, and I can ask you all kinds of questions, but let's start off with one that might not be the question you think I'm going to ask. But let's see. What is the limit of this function as x approaches 0? Okay, so what we want to do is we want to think about the graph approaching 0. So here, right here is 0 on the x-axis, and we're going to approach it from the left side. We're going to approach it from the right side, and you'll notice that the two sides are coming together right here at a y value of 1. Now, yes, there is a point there, right? There is a point at 0, 1, but the presence or absence of that point doesn't really matter. But what matters is that as we get closer to 0 from the left and from the right, we're coming together at 1, and that's the limit. Pretty easy. Now let's ask about 2, because we clearly see something funky happening here at 2. So what is the limit as x approaches 2 of this function? All right, so this is where we really have to open our eyes and look. So first off, I do see that there is a point at 2, 1. But again, the presence or absence of that point doesn't really impact your answer at all. But here's the deal. Look at the left side. As I approach 2, right here, sometimes it actually helps to draw a dotted line at 2. I'm serious. I still do this sometimes. Draw a dotted line at the x value that I asked you about, which in this case is 2. And then approach that dotted line from the left side. And I'm up here. and approach that dotted line from the right side. And I'm down here. And I'm like, whoa, wait a minute. From the left side, I'm up here at 4. From the right side, I'm down here at 1. They're not coming together. The two sides have to come together. The left side and the right side have to be coming together. They don't have to actually meet. There could be a hole there, but they have to be coming together. So this is a great example where the limit does not exist. It just doesn't exist. The left side and the right side aren't coming together. Remember, that's the definition of a limit. For a limit to exist, you have to be approaching the same number from both sides. And on the left side, I'm approaching 4. On the right side, I'm approaching 1. Well, it's not matching up. So it's a great example of a limit that does not exist. All right, let's take a look at a line, right? This is just a plain old line, red line. Okay. And I could say, all right, what's the limit as x approaches 2? Again, use my dotted line method. Sometimes it does actually help. So here is 2 right here on the x-axis. So draw a line there. And we could ask ourselves, is there a pointed 2? And there certainly does appear to be a point at, looks like 2, maybe 3.2, 2, 3 point something, 3.2, whatever. But the point is that that's not necessarily the answer. So I like to examine that. I like to consider that, but that's not going to necessarily be your answer. Not always. So when I talk about, limit is saying, don't talk about at 2, talk about getting closer to 2. So here we are getting closer to 2 from the left. Here we are getting closer to 2 from the right. And the good thing is my two sides are coming together. They're coming together right here. And that looks to be about, 3.2. Now, again, if you said, oh, that looks like 3.4. Okay, whatever. We're not a big deal here. But you get the point is that they got to be coming together. The two sides have to be coming together. And the nice thing about a line like this is true for any point. So, for example, if we asked about the limit as x approaches -4 right here. Here's -4, right? Notice the left side and the right side, they're coming together right here at about -1.3 maybe. But the point is at any point, any x value on this line, the two sides are going to come together, so you will have a limit. All right, let's do another one here. Try to keep this nice and easy, just try to show you exactly what's going on here. All right, so this is talking about the limit as x approaches -3. Once again, sometimes it does help to kind of draw that line at -3. And you follow the graph on the left side. You follow the graph on the right side, and the two sides are coming together, right? The two arrows are meeting. We need that to happen. And where are they meeting at? Well, if you erase all the crap in this side half here, it does look to be about 1, 2, 3, 4. It actually looks to be just short of 5, so maybe we'd say 4.8 there. Again, if it's a graph, I'm going to be okay if you can do a little bit of rounding in your mind. There'll be a little bit of a range of answers I'd accept. But somewhere right around here, again, limits are y values. It's about a y value of about 4.8 or 4.9. All right, here's another example. It's asking us what is the limit as x approaches 1. So once again, here is my line at 1. And the left side is going to here. The right side is going to here. Best news in the world is my two sides are coming together. And it looks like they're coming together at 2. So there's your answer right there, 2. I mean, how easy is that, right? Really simple. All right, here's a tougher one. But I think you're going to like the results. All right, what is happening to this function? What is the limit as x approaches -2? So once again, let's go ahead here and make a line at -2. And we say, okay, well, on the left side, it looks like I'm going, looks like I'm going up forever and ever and ever. The right side looks like, it looks like I'm going down forever and ever. So I noticed two things. One, they don't come together. So right away, the limit does not exist. But I actually noticed that this is a vertical asymptote here. And as you approach -2, the limit just doesn't exist because the two sides, the left and the right side, are not coming together. And that's how you identify what a limit is, right? You examine, don't examine what happens at -2, in this case, nothing, but you're examining what happens as you approach -2, and they got to be coming together. They got to be meeting at the same y coordinate, and that's just not happening here at all. Now, that's just one spot. A lot of kids will think that the answer to any limit question when there's an asymptote doesn't exist. Listen, I asked you about -2. That's where clearly the limit does not exist. But watch out, right? I could say, what's the limit as x approaches 2? +2. Okay, well, +2 is right here. And at +2, The left side is coming here. The right side is coming here. And it does appear that they are coming together at maybe negative 0.5. So there would be your answer there. So this graph has one spot where the limit does not exist, but any other x value, the limit would exist. So again, we like to kind of point out the negatives when we look at these graphs, right? We like to point out the things that look interesting. But for every time there's something that looks interesting, there's lots of things that are just very non-interesting because the limit exists and it's beautiful and it's perfect. All right, here is another one where something strange kind of happens, but we should know exactly how to deal with this. So we're looking at what is the limit of this function as x approaches 2. So once again, put a line at 2. And you say, okay, the left side coming here, the right side coming here. Good news, the points are coming together. The points are coming together at a y value of 2, so there's your answer 2. But what I want to note here is this is a great problem to realize that at 2, D, and E. Nothing exists at 2. There's clearly a hole at 2. And that is, again, why I've tried to say as many times as I possibly could, that the presence or absence of a point at the value that's in question doesn't matter, right? Like here, there was no point, but there is still a limit. And in other problems like this one, there was a point there, and that was the limit. Okay, great. So sometimes there's a point there, sometimes there's not a point there. That doesn't impact the answer to the limit. And that's why a limit is truly a different question than anything you've been asked before. So hopefully you understand that one. All right, here's another example. We actually have two questions here. So the first one is saying -2. What is the limit of this function as x approaches -2? All right, here's an x value of -2. And as I approach -2 from the left, as I approach -2 from the right, they're coming together at 2. Awesome. Now, even though there's no point there, oh well, they're still coming together from the left and right-hand side. Because remember, a limit's not asking you what happens at 2. So what happens is you approach 2. All right, now let's do +3. Here's +3 right here. Left side here, right side here. They are coming together, and there's a point there. Added bonus, there didn't need to be a point there, as we saw with the other example, but they are coming together at a value of 2. So both of these have a limit of 2. All right, here's another one. Pretty weird looking function here. All right, so what's happening here is we're asking about the limit as x approaches -2. So here's -2. And the left-hand side is down here at 2. The right-hand side is up here at 4. Uh-oh, they're not coming together. Another example of a limit that does not exist. Pretty easy, right? Hopefully you guys all make sense of that. Again, they've got to be coming together as you approach from both the left and the right-hand side. So let's look at some possible situations here, right? Because we just looked at tons of examples. Everything was a little bit different. Something a little bit different happened. So we really want to look at the different situations that can occur. So notice at this example right here, if we're asking you about, let's say we're asking you about 2, the value 2. What is the limit as x approaches 2? Of this function. All right, so notice that a couple things. First off, the f of x does exist. There is a point right there at 2, 4. There is a point there. And the two sides are coming together at that point. So there is a limit. The limit does exist. The limit does exist at 4. So this is an example where there is a point at 2, 4. But remember, the presence or absence of that point does not determine the limit. But I just want to make sure you note this is a situation where there is a point there and the two sides come together at that point. Life is beautiful. Life is great. The limit does exist, in this case, at 4. All right, now here are a couple other situations where f of x does not exist at L. So there's a hole, right? So look at this graph on the left here. There is a hole at 2. Looks like it's at 2, 7. There's nothing there, though. There's a hole there. But the left side and the right side do come together at that value. So the limit as x approaches 2 of this function looks to be 7. So this is a good example where there's a hole there, but the two sides are coming together, hence the limit does exist. Here's another example. This is actually called displace point. So we took the point that was supposed to be at 1, 4. There was supposed to be a point right here at 1, 4, and I just moved it. So this is a good example where there is a point at 1. It's just down here at 2. 1, 2. There is a point at 1, 2. So we moved the point. All right, weird, but whatever. So the idea, though, is, that's the limit. The limit is asking you what happens. You approach 1. So from the left side and from the right side, the limit as x approaches 1 of this function is 4. So again, even though the point existed down here, that didn't matter. Remember, limits aren't asking you, hey, what happens at x equals 1? They're asking you what happens you approach x equals 1. And as I approach x equals 1, the limit, the two sides, are coming together at 4. All right, now here we see something that we've talked about in the past. This is a jump. So here, if we're talking about, first off, a couple things. So at -3, so if we're asking about the limit as x approaches -3, and they're calling this h of x. Well, all right, great. Who cares? All right, so what's happening as we approach -3? So first I want you to note there is a point. There is a point right there at -3, 2. But remember, the presence or absence of that point doesn't matter to the limit, because the limit's saying, hey, if you're going to approach -3, left side is up here at 6, right side is down here at 2. Uh-oh, the limit does not exist because the two sides are not coming together. All right, here's another situation very much like the one we just saw, but this time there is no point. Right here, the left side approached 6, but there was an open hole there. The right side approached 2, but there was a filled-in dot there. Okay, the limit still did not exist because the two sides are not coming together, but at least there was a point. Excuse me. In this example, there is no point. So what happens at 3? Nothing. D, N, E. There is no point there, but does the limit exist? Well, left side's down here at 2, right side's up here at 3. They're not coming together. So no, the limit does not exist at 3 for this example. All right, here's another example where we see this infinite thing, this vertical asymptote, right? So if we're asking you about the limit as x approaches 2 of this function, we notice a couple things. First off, there is nothing at 2. But once again, or maybe not once again, my gosh, the 10th time I've said in this video, the presence or absence of a point at x equals 2 doesn't matter to the answer of the limit. It's all about what's happening as we approach 2. And from the left side, we're way down here at -infinity. From the right-hand side, we're going way up here to +infinity. They're not coming together, hence the limit does not exist. Now, in the previous video, we talked about analyzing these problems kind of analytically on our calculator. We actually did see this, right? We saw that as we approached from the left side, we were going really, really low. -1,000, -10,000, -100,000, -1,000,000. We're just going lower and lower and lower. And from the right side, we were approaching +infinity. 5,000, 20,000, 30,000, 100,000, 1,000,000. We're just going forever and ever up. But again, the main thing here is that the two sides are not coming together, so the limit does not exist. All right, so those are all the different kind of situations where sometimes the limit does exist, sometimes the limit does not exist. So hopefully graphically you understand all those and can easily decipher what is going on, again, for a given value that I asked you about. So let's end this video, we are almost done, with one final graph that really kind of has everything. This is really a cool graph, and here it is. And graphs like this are basically piecewise functions. They're made up of a bunch of different pieces and parts of functions all put together. And these are the greatest functions to talk about because there's just so much to talk about. So let's just kind of run through a gambit of questions I could ask you. So I could say, hey, what is the limit as x approaches a of this function? Well, here's a right here. And we say, okay, as we approach a from the left, we're going down. As we approach a from the right, we're going up forever. Well, by golly, this is what we just looked at. It does not exist. The limits, the two sides, the left side and the right side are not coming together. And there's nothing even at a anyway. All right, what is the limit as x approaches b of this function? Well, at b, which is right here, we see the left side is down here somewhere, maybe around 1. The right side is up here, maybe somewhere around 1.5. But once again, we see kind of that jump where the two sides are not coming together, hence does not exist. All right, what is the limit as x approaches 0 of this function? Well, 0 is really the y-axis right here. And we say, okay, as we approach 0 from the left side, we're down here. As we approach 0 from the right side, we're down here. So it looks like the limit does exist. The two sides are coming together, maybe negative 2.4. Negative 2.4. Again, that's the y value where they're coming together. Now, I want you to notice that there is a point at 0, but that point is way up here at 0, 1. But that point doesn't matter. It's all about approaching 0 from the left and right and coming together. All right, what's the limit as x approaches c of this function? Well, you've guessed it. Doesn't take too long to look at that one. Once again, another does not exist. Here's c. Left side's up here. Right side's down here. They're not coming together. Heck, there's a point way down here. But once again, the presence, or for the final time, the presence or absence of a point at x equals c doesn't matter to the limit as we approach c. We need the two sides to be coming together. So we see A, B, C, and then again 0 I asked you about here. And you kind of see the full gambit of all the different things that can happen. It does not exist due to an asymptote. It does not exist due to a jump. An existing limit, even though there's a hole there, and another jump right there. Okay, so pretty cool. But I want to finish off with one more thing here, right? Let's just add a new value here. We'll call it d. And I said, okay, there it is. What is the limit as x approaches d of this function? Well, once again, there does appear to be a point at d. But remember, I said it was going to be the last one, but I'll say it one more time. The presence or absence of that point doesn't matter for the limit. But check this out. As I approach d from the left side, bingo. As I approach d from the right side, bingo. Look, the two sides are coming together, and it looks to be, I don't know, maybe a y value of, let's just say 0.9, pretty close to 1. But again, they are coming together. So again, this graph has a lot of interesting features, a lot of places A, B, C, where the limit does not exist. It has a place at 0 where there's this displaced point, but the limit does exist. But for all of those points where something weird happens, there are plenty of points where something non-weird happens, and the limit certainly does exist. So be ready for all those different things that can happen, and all those different kind of things you got to be available to look at when you analyze one of these graphs. All right, guys, see you in the next video.